Good evening, viewer. Welcome to our Glory Globe TV. Here's a breaking news. Yes, researchers confirm theory of quantum frictions. Water and carbon make a quantum couple. The flow of water on a carbon surface is governed by an unusual phenomenon dubbed quantum friction. A recent study provides experimental proof of this phenomenon previously predicted through theoretical research occurring at the interface of liquid water and graphene, a monolayer of carbon atoms. The research was conducted using advanced ultra-fast techniques. These results could lead to applications in water purification and desalination processes and maybe even in liquid-based computers. For the last 20 years, scientists have been puzzled by how water behaves near carbon surfaces. It may flow much faster than expected from conventional flow theories or form strange arrangements such as square eyes. Now, an international team of researchers from the Max Planck Institute for Polymer Research of Mainz, Germany, the Catalan Institute of Nanoscience and Nanotechnology, ICN2, Spain, and the University of Manchester, England, reports in a study published in Nature Nanotechnology on 22nd June 2023 that water can interact directly with the carbon's electrons, a quantum phenomenon that is very unusual in fluid dynamics. A liquid such as water is made up of small molecules that randomly move and constantly collide with each other. A solid, in contrast, is made of neatly arranged atoms that bathe in a cloud of electrons. The solid and the liquid worlds are assumed to interact only through collisions of the liquid molecules with the solid's atom. The liquid molecules do not see the solid's electrons. Nevertheless, just over a few years, a paradigm-shifting theoretical study proposed that at the water-carbon interface, the liquid's molecules can the solid's electron push and pull on each other, slowing down the liquid flow. This new effect was called quantum frictions. However, the theoretical proposal lacked experimental verification. We have now used lasers to see quantum frictions at work, explains study lead author Dr. Nikita Kavakin, a researcher at the Max Planck Institute in Mainz and the Platerion Institute in New York. The team studied a sample of graphene, a single monolayer of carbon atoms arranged in a honeycomb pattern. They used ultra-short red laser pulses with a duration of only a millionth of a billionth of a second to instantaneously heat up the graphene's electron cloud. They then monitored its cooling with terahertz laser pulses, which are sensitive to the temperature of the graphene electrons. This technique is called optical palm terahertz probe spectroscopy. To their surprise, the electron cloud cooled faster when the graphene was immersed in water, while immersing the graphene in ethanol made no difference to the cooling rate. This was yet another indication that the water-carbon couple is somehow special, but we still had to understand what exactly was going on, Kavakin says. A possible explanation was that the hot electrons push and pull on the water molecules to release some of their heat. In other words, they cool through quantum frictions. The researchers delved into the theory, and indeed water graphene quantum frictions could explain the experimental data. Beyond the report, Glory Globe TV, Delhi, India.